welcome here to the Quantum Speaker Series, sponsored by or hosted by the ATARC's Global Quantum Working Group. I am Jason Lee, one of the government co-chairs for the working group. I am excited to welcome Geraldo Ortiz and David Stewart to speak with us today. David is the executive director of the Purdue Quantum Science Quantum Science Engineering Institute, and Geraldo is a professor of physics at Indiana University, scientific director of IU Quantum Science Engineering Center, and IU site director for the Center for Quantum Technology Technologies. We're here to talk today about an overview of the Center for Quantum Technologies. If you have any questions, please use the Q&A feature. And David, take it away.
Yeah, thanks so much, Jason and all, for the invitation to speak today. We're excited to tell you a little bit about our center, which is the Center for Quantum Technologies. Let me start sharing here. Okay. So as Jason mentioned, I'm the executive director of Purdue's Quantum Science and Engineering Institute. I also serve as executive director for this Center for Quantum Technologies, as well as the industry liaison officer for this center. And so the Center for Quantum Technologies is a partnership between Purdue University, Indiana University, and the University of Notre Dame. So very Indiana-centric, of course. But we came together many years ago, and I'll show a timeline here in a little bit. But we were awarded a planning grant from NSF to work on this center, and then received a Phase 1 award in August 2022. So I'll sort of walk you through what this center is and the framework, and then Gerardo will take you through some of the research aspects and other activities ongoing. So our center is an Industry University Cooperative Research Center, acronym IUCRC, which is a NSF, National Science Foundation program to catalyze pre-competitive use-inspired research. And they really have three goals in these centers that NSF sets forth. One is to conduct high-impact use-inspired university research to meet needs of the membership. The second is to enhance U.S. global leadership in driving innovative technology development. And last is to identify, mentor, and develop a diverse and highly skilled workforce, which for quantum science and engineering is critically important right now. So here's a figure that I've just kind of stolen from NSF that shows how these centers work. NSF and also other government research entities can be involved. NSF provides financial support and oversight of the center, but other government agencies are also involved in these. Universities have the world-class infrastructure, people, technical expertise to carry out the research projects, and the industry members provide funding for the research efforts and help guide us along the way to do industry-relevant research projects. So IUCRCs really lie between, very basic early-stage research and commercial deployment. So we sort of lie in that gap there in technology readiness, trying to bridge basic ideas out of the lab into commercially viable products. So here's our leadership team. Each university has their own site director. So at Notre Dame, it is Professor Peter Kogi. At Purdue, it is Yong Chen, who is also the overall center director, as Purdue is the lead site for this center. And then Gerardo, who is here with us today, is professor at Indiana University and serves as their site director. As I mentioned, I'm the industry liaison officer, which is an NSF coined term, and executive director for this center. We also have Indianapolis campus of Indiana University involved, and Professor Ricardo Deca leads the efforts there. So as I mentioned before, all located in Indiana, we have a great experience working together and collaborating and really make up a great confluence of quantum science and engineering excellence here in the state. So here's our timeline of what we've been through to really launch this center. So it's been a long process. We started late in 2019, early 2020, planning the center, held multiple workshops, and presented a planning grant proposal, which was awarded in May of 2021. And with that, NSF just gives us a little bit of funding to sort of investigate these centers, do interviews with industry members, attend some training to learn how to most effectively run these centers, held a meeting out of that award, and then we submitted our phase one proposal in December of 2021, which was awarded in August of the next year. So we held our inaugural launch meeting in February of 2023 at Purdue, and then our projects launched later that spring. So we're now into our second year of research projects, which just started in May of this year. So IUCRCs are primarily made up of for-profit industry, but they can also include not-for-profit organizations, state and local agencies, other government agencies. They form an industry advisory board, which is one representative from each member sits on that board. There's a single membership agreement that NSF mandates everybody sign. And then a very unique aspect of these centers is that the members actually get to select projects in a collective voting process. So the members pool their annual membership fee, which goes 100% to research efforts, and then select the projects within the center each year. So our membership fees are here. They've somewhat strange numbers as they've gone up by a little bit of a few percentage points here in the last year. But there's different membership levels. Most are signed up at a full membership, which gives you one vote. But there's other levels which just give you different voting rights when it comes time for project selection. And so NSF provides funding for all the admin and management costs. They support staff salaries and faculty salaries. They cover meeting costs and travel, publication costs, things like that. And then the members provide funding for the research. And a great part of these centers is that there's no overhead on all the member fees. Every dollar that our members put in goes 100% to fund research efforts within the center. And then the universities have great infrastructure, wonderful faculty and researchers to conduct the research. And out of that, the members get access to the pre-competitive research results and the highly skilled workforce that we're developing. Significant value in a number of different areas. So access to talent is, of course, one. There's opportunity to work closely with our students. And this is a statistic that's pulled straight from NSF that 25% of students who work in the IUCRC program eventually become employed by member companies. And I should mention that there are about 80 of these centers across the country, 80 IUCRCs. Ours is the first one focused on developing quantum technologies. Another value proposition is risk mitigation. You're sharing the risks of this early stage research with peers within the field. Lower research costs. Of course, the universities already have great facilities in place. You're funding, providing support for a grad student, which is much cheaper, of course, than hiring a brand new full-time employee. You're leveraging those research dollars as they're being pooled, getting more bang for your buck, which I'll talk about more on the next slide. Certainly networking opportunities with the other members, but also with our faculty and students. And then all members of the center get royalty-free, non-exclusive licenses to any IP that's produced. And so I mentioned the leverage on the investment. It's very significant. So our full membership level, actually need to update this a little bit, is slightly over 50,000. So we currently have 8 full equivalent members, which comes to 420,000, coupled with NSF's funding provides about 870,000 a year for this center. So, you know, a full membership fee is about a 16-to-1 leverage on your investment right now. Another thing I like to mention is that we can apply for supplemental funding opportunities through NSF. And one of the very attractive ones is their intern program, where NSF will actually cover the costs for students to come and intern at member organizations for up to 6 months. So it's a great benefit of working in this center. So here's sort of the yearly tempo that we have within the center. And I'll start on the bottom here with our spring meeting, which coincides with our project selection. So at that meeting, our faculty from across the 3 universities come together and they pitch projects to our industry advisory board during that day. And then, as I mentioned, the industry members collectively vote on which ones get funded. The projects launch, and then 6 months later, we do a project review where those projects that were funded give an update on their progress. But almost a more important part of that meeting is that we really go into great ideation with our members to plan for the next round of proposals that'll come in. So we get good feedback from our industry and government members on what they'd like to see in the next round of projects, and that helps us guide our solicitation that's sent out to our faculty later after that meeting. So throughout this project, or throughout this process, we have continuous dialogue with our industry members. They serve as mentors for a number of the different projects. And because they get to vote, on which projects are funded, they really have a lot of say in the research direction of the center. I don't want to read everything on this slide, but this is just to highlight the breadth of expertise that we have across the 3 universities. We have over 100 faculty working some area of quantum information science. It allows us extreme flexibility in being able to meet whatever needs our industry advisory board members have. And so here's our roadmap. Again, we have expertise in a number of different areas, but the center focuses on really these 5 key themes, which are algorithms and architecture, materials design and chemistry, communications and networking, finance and business, and sensing and hardware. So we really want to lie in this area on the left here, where the needs of our membership overlap with the expertise of our faculty and researchers. So that's really our sweet spot. And then out of this, the members get access to the pre-competitive research results, the highly skilled workforce we're developing, and hopefully brand new state-of-the-art quantum technologies that we'll develop. Quantum is, of course, very important for our country. The center directly follows several of the efforts that were described in the National Science and Technology Council's strategic overview for quantum information science, which I believe came out in 2018. So one of those is focus on a science-first approach, certainly doing that at research institutions, build a quantum smart and diverse workforce. I've harped on this already a lot. We're developing talent, getting use-inspired experience as they work on these research projects, and then encourage industry engagement, which happens just by the framework of the center itself. So we're really growing an awesome ecosystem, enhancing the country's quantum collaborations and partnerships, knowledge, and workforce development efforts. So here is our current list of membership. It's quite diverse. We have folks from DoD, pharma, automotive. We have niche quantum computing companies, quantum networking companies. So it's a really wonderful mix of folks that are coming together maybe in ways they wouldn't otherwise if this center didn't exist. So it's great in forming new partnerships and exciting collaborations amongst our membership. Before I turn it over to Professor Ortiz, I just want to show our list of year 2 projects. So we really have great representation across all 3 universities and across all of our key research areas within the center. So diverse not only in our the universities participating, but in the research themes within the center. So that's all I have, and I will turn it over to Professor Ortiz. If you have any questions about the center framework or want to learn more about membership, please reach out to me either at cqt@purdue.edu, or you can contact me directly, davidstewart@purdue.edu. So with that, I will stop sharing and pass over to Professor Ortiz. You're muted, Gerardo.
Okay, so hello everybody, and thank you, David, for your presentation. My name is Gerardo Ortiz, and I am the IU Indiana University Site Director for the Center for Quantum Technologies. And my task today is to guide you through the science behind our value propositions. So before telling you in more detail about this science, and since this is a very broad audience, I will try to tell you a little bit what is the intellectual thread behind the center. So let me start telling you and defining what is quantum information science and technology. At the risk of being a little bit pedantic, but I would like to explain the real science behind this enterprise. So the quantum information science and technology is a field of research that what it does is to exploit the fundamental laws of quantum mechanics. So most of the technologies that we are used to are essentially exploiting the laws of classical physics. But it turns out that the laws of quantum mechanics allows you to reach certain performances in complexity and efficiency, which are beyond the things that we are used to in classical physics. So it turns out that among these things, we can say that we can exploit something that is called a state superposition, which is some sort of interference effects, something that is defined in the second quantum revolution, that is the property of entanglement, and also the property of quantum measurement, something we do not have in classical physics. So the idea is to exploit all these different traits of quantum mechanics that to our advantage, in the sense that we can essentially perform certain things and certain operations that are hard to perform in the classical world. And indeed, this already started driving a revolution in different fields like communication, computing, sensing, etc., as you have seen in the news. So as David already said, this indeed is a very multidisciplinary field of research. And that means that it involves completely different aspects of science and technology. And it turns out that our center essentially has a very deep breadth in this field. Now, we have divided this particular field in 5 different sections. Indeed, these sections have already been mentioned by David, but it turns out that indeed these sections are not, completely independent, and there is a lot of overlap with these different divisions. As you will see in the proposal that I'm going to highlight in today's presentation, you will see that many of the things have a lot of overlap. For instance, you can see proposals that are developing new materials, but these new materials indeed are exploited for quantum sensing. So you can see that indeed these two sections are going to overlap strongly. So, as already mentioned, we have over 100 faculty that are working in all these different aspects. So how is that we choose all these different proposals or value propositions? So indeed, what we try to do is not only to emphasize the science, but that science that is not only fundamental, but is transformative and can have lots of technological applications. Indeed, we try to create a community with the industrial partners and academic partners in a way that we can work together even outside the center. So let me put as an example, how is that we work with this value proposition? Typically, what we do is we select a certain number. I mean, the universities, our centers select a certain number of oral presentations that essentially covers all these different subfields. And at the same time, we have a set of posters that are presented by students. Okay, those posters essentially, they are either extensions of this oral presentation or new ideas that we believe that in principle, maybe the industry is not completely, interested at the moment, but, you don't know. So they are there. So all this is based on the interaction we have with the industrial members. And indeed, this is our best guess of what is of interest to them. So let's put as an example, for example, our year 1. In our year 1, we presented these 15 value propositions that covers all these different areas. for instance, algorithm and architecture, and we have all kind of proposals that essentially covers software and hardware aspects of this thing. So, but we also have, applications in finance and business, and these are mostly, algorithmic applications. Or we have things that are directly related to material design and chemistry that may involve, the use of NISC devices for simulation of quantum chemistry, for example, or it could be the development of new materials for sensing. Or we have, explicit quantum sensing and hardware, where, for example, we are trying to develop better single photon emitters and entangled photon sources for communication. Or we may have also proposals that are addressing issues on quantum communications. So the idea is that, we have these presentations in the spring, and after the presentations, there is a selection, and the selection typically, these are of the order of 6 or 7 proposals. And this selection is made by the Industrial Advisory Board. And as you can see here, for example, out of these 15, these 7 have been chosen, and they cover mostly, almost all these different areas in quantum information science and technology. And, all these universities are indeed represented. So you have some proposals, like for example, the proposal on materials for future quantum architectures that involves almost all the universities. But there is another aspect that David mentioned before that is important to emphasize, is that the industry not only chooses the proposals, but also they have a mentor role in this whole thing. And here you are seeing how these different industrial partners and members, they are choosing, some, 2 or 3 of these proposals where they want to be advisor or mentors. And they interact very closely because there are very close relation between the industrial partner and the center. So let me now give you, just quickly, some sort of flavor of what happens after, essentially 1 year. So after these projects have been chosen, indeed, the center starts working. There are students, postdoc involved, faculty, several universities, as we have said here. In some cases, there is a overlap between these different sub areas. And indeed, let me explain briefly, what happens, for example, in one of these proposals, that a proposal where all universities, the 4 universities, are involved. Okay, so what happens is the following. Indeed, given the breadth of all these 4 universities, we can attack this problem from many different angles. And these different angles are, either the growing of materials. In this particular case, we have been working with these bismuth telluride selenide materials to build wires, quantum wires. And these quantum wires are fabricated, and they are fabricated in a way that they exploit a particular property that is called magnetochiral anisotropy, such that this particular property allows you to enhance sensing, quantum sensing. So the idea is that you want to design these wires in such a way that you can sense with high accuracy, very tiny electromagnetic fields. But at the same time, we have also people working in theoretical models and people using, for instance, density functional theory to essentially study from first principle these materials, okay? And that helps the experimentalists to essentially apply the desired control to improve that sensing quality. Okay, so this is one of the proposals. So I could be talking about other proposals. For instance, let's talk about this proposal on quantum sensing, a specific quantum sensing, that the idea was here to design single photon emitters. High efficiency single photon emitters. And indeed, this is what this particular proposal discovered. That is, they could, with silicon nitride films on silicon dioxide, they could produce room temperature single photon emitters. And of course, they have applied these single photon emitters in different architectures and for different applications. For instance, for quantum key distribution. You know, I mean, I can continue. I mean, there are proposals on quantum software, and this quantum software proposal, for instance, they've been trying to benchmark the different NICE devices, and essentially by addressing their performance for specific problems. Like, for example, combinatorial optimization problems like graph partitioning, okay? And they try to use all these different NIST devices, and they try to see how the performance for this particular problem with system size, et cetera, how is that it works, okay? So the question is, what happens after 1 year cycle? Okay, so what happens after 1 year cycle is exactly this, is the product. And in the products, you can see here what is that it has happened. So essentially, the center that is represented by the 3 universities, they have produced of the order of 14 papers, okay? Some of them, they are in preparation or submitted, okay? But that's not the only thing. Indeed, there is something very important, that is the quantum workforce, that in principle is not just the quantum workforce that involves people in college, in university. Indeed, we've been working very, very closely with high schools, and indeed even middle schools. And because we would like to have some sort of, you know, community of educators in high school and middle school that can transfer this knowledge at an early stage, okay? Because that's extremely important, because, you know, we will have people outside working in industry pretty soon in this way, okay? So indeed, we have been doing that very efficiently in the state of Indiana, and indeed we receive teachers from other states also. I mean, this was not restricted to the state of Indiana, but we also have outreach type of activities with high schools, okay? So this quantum workforce development is extremely important for this type of science and technology. So the year 2 projects, so this is the new projects that we have now. And as you can see, these projects now are, you know, some of them are some sort of continuation, like for example, the first 2, where now they are benchmarking not only NISC devices, but also hybrid quantum computing. So quantum computing that not only, you know, is exploiting these quantum devices, but also classical computers. So that's the reason why it's hybrid, is classical quantum hybrid. But we also have proposals that, you know, they are quite interesting and is transformative and is going in directions that are not, you know, in principle so natural within this kind of thing. Like, for example, this quantum natural language processing, okay? And machine learning and, you know, quantum artificial intelligence. So let me tell you what this kind of thing is, just to see what is the depth of our approach to this problem. So, you know, I mean, here in this kind of thing, what we are trying to do is to develop, you know, coding and libraries, and indeed develop sophisticated models for encoding meaning and semantics. You know, this is something that is highly non-trivial, and it's something that, you know, in the classical work, they already started doing this kind of thing, but now incorporating the quantum work becomes extremely interesting. So with this, I mean, I would like to stop here. And I would like to now take questions, I mean, for David or for myself. Thank you very much.
All right, thank you both for that great presentation. We do have some questions, and David, I see you've gotten there and answered some of them, so I really appreciate that. The ones I still see open are, is there anything you would consider required reading in this space, white papers, books, keynote speeches, memorandums, or anything like that?
So I may answer that
Yes.
question. Well, it depends, at which level. Of course, there are lots of things you can read. There are some very interesting and simple presentations. Like, for example, there is a book that it's very elementary that is called Q for Quantum. Okay, this book, Q for Quantum, indeed presents quantum mechanics without any kind of math. And it's essentially trying to give you an idea of in which ways these differ from your classical reasoning. Okay, so that's a very good place where to start. Now, if you are more sophisticated and you have mathematical knowledge or physics knowledge, of course, there are more advanced books, and I am willing to give you all kind of details about that. If you want, you can send me an email, and I can give you, depending on your level, what kind of reading is useful for you.
Thank you. David, do you have anything to add to that question, or?
No, Gerardo's probably the expert there, but quantum is quite broad and at various levels, right? So there's all kinds of content out there that you could read.
Thank you. The next question I have here is someone says they're curious to learn. I think it was Gabriel. I'm curious to learn more about the cybersecurity implications of your team's quantum research.
So again, I mean, we have several groups working on different aspects of quantum communication and security. So we have in our group people working on post-quantum cryptography at Notre Dame, for example. So we have people working. So that means this is mostly software, if you will. But we have also people working in hardware, and people not only developing new sources for entangled photons, and this is a crucial technology that we need for secure communication. Not only developing these entangled photons, but also developing smart fibers. So fibers where we can incorporate quantum components in the fiber. So that is a kind of very new thing. I mean, this is an idea that is on the works. It's not that we have, quantum components inside the fibers that are working at the quantum level at this moment, but we are going in this direction. So, and then, we have lots of quantum opticians also working either in the context of either fiber communication or free space communication. So again, if you want more details, we can refer to these people.
Thank you. I see another question I have, and I'm not sure exactly what the ask is, but I'll read it. It's how are you getting the high school students and teachers involved?
Yeah, so I can start, and then I'll hand it to Gerardo. So one thing focused on students is CQT graduate students working within the center went to Southport High School, which is on the south side of Indianapolis, over 2 days, and we trained over 200 students, at least exposed them to quantum, right, and the different themes within quantum. So that was one thing that we've just started. That was in April. We hope to continue to do more things like that, but it was in partnership with Qubit by Qubit, which is a nonprofit which provides educational training opportunities for students at all levels. And then we did another training session with teachers, which came out of Indiana University. So maybe I'll let Gerardo tell you about that one.
Yeah. Yeah. So let me say the following. Let me say that indeed, US is not the first country trying to educate high schoolers. Okay, so these ideas started in other countries like Singapore, for example, many years back. Indeed, there is a book, I mean, from Singapore, written for high school students. Quantum mechanics or quantum physics or quantum information science for high schoolers. Now, what we've been doing here was the following. We've been trying to, instead of going ourselves to high schools, that we can do that, okay, we can do that, but instead of doing that, what we've been doing is we train the teachers. So what we did is we have some sort of boot camps where the teachers come for a couple of weeks or 3 weeks. They are coming from different, in this case, in our case, coming from different states. Indeed, they were of the order, I think, I don't remember, but among, there were also undergraduate students, graduate students and teachers. And this was an enterprise of, maybe 20 people, around 20 people. I don't remember exactly the numbers. But the idea is that you try to, and in this sense, I must say that Adrian German has been fundamental in this role. He's a guy working in the computer science at IU, and he has been trying to teach this science at a very elementary level with very low mathematics, very, very low mathematics, and something that, the teachers can understand very well. And then from there, then they write together. Okay, they write together white papers saying what needs to be done, okay, in other high school to teach this science. So this is extremely important. I mean, I don't know how much I need to emphasize the importance of doing that in our high school all over US, not just in the state of Indiana or whatever. All over US, we should start doing that because this is a new way of thinking. And you need to get these guys to think in this way so that at the very early stage is going to be something very natural to do.
Thank you. Thank you. Let's see, the next question I have is, what is the cost of different membership levels? Are proposals for research projects only accepted at certain times of the year?
Yeah, so to the first part about the membership levels, our full membership level is just over $50,000 right now. That's an annual membership fee. There's an associate level, which is half of that, just over 25,000 right now. And then there's also a double membership, which is just over 100,000. And so the difference in those is the voting rights the members get when it comes time for project selection. So our industry members, if you pay for a full membership fee, you get 1 vote. If you pay for an associate, you get a half vote. If you pay a double, you get 2 votes. So that's really the only difference in those. Our proposals, after our project review meeting, which we also use to work with our industry members to really get their input on what types of projects they would like to see. That's in the fall. We then solicit our proposals from our faculty members at that point. And so we accept proposals then in early spring each year. And then those are presented to our industry advisory board at our spring meeting. And then they go on to select those during that meeting. And then they're funded for 1 year. So we just have a rolling cycle. Projects can be renewed, of course, but we also allow new proposals to come in each year as well. I just saw the new question come in. So we only accept proposals from our faculty. So only university faculty that are members of the center, so from Indiana and Notre Dame and Purdue, are allowed to submit proposals. So all the research within the center happens exclusively at the universities with guidance and input from the industry members.
Thank you, David. All right, the last question I see right now is, how close are we to commercialization of quantum key distribution, and will it be available in a few years? I'm assuming that's for Geraldo. Or Geraldo.
It depends what you mean commercial. I mean, it already exists. Okay, there are companies that they said they sell these QKD things. The big challenge is to have QKD systems that can be established at very, very long distances. You know, we can put, you know, communication system that can go around the Earth. That would be the ideal. So we are not there yet. Okay, we are not there yet. So now, from our perspective, I mean, we are trying, and this is one of our proposals, indeed, for one of, you know, the NRT NSF proposal that we are submitting now, is we are trying to establish some QKD among universities. Okay, and indeed, there is a I would say a company. You can correct me, David. There is a company called Quantum Corridor that they are trying to establish a quantum network that is going from Chicago to Ohio. Okay, so these things are in the works, but you realize that even going from Chicago to Ohio is a challenge, okay, because this is not free space. This is fiber optics. It's a real challenge. So going around the Earth, it's a much bigger challenge. But there are commercial. I mean, I'm not going to give names of companies, but there are companies that where you can buy some QKD sets. I mean, which basically amounts to getting, you know, a good, you know, good sources of photons and single photon detection.
Thank you. Let's see. Let me back up. Do we really expect to route with quantum without IP addressing?
Without IP addressing, I don't know what it means exactly. So supposedly with quantum, we would like to have, you know, quantum security. So, I mean, quantum security means that you can basically, if there is an attack, you can figure it out. Okay, you can figure it out that you were attacking in the channel. But I don't understand what it means without IP addresses. I mean, exactly. So I don't understand that particular statement.
All right, Amy, I think that's all the questions are in the Q&A. I'm actually disconnecting Q&A. Oh, it's finally back up. But yeah, that's all the questions we have. Pending anything else, I really appreciate y'all joining us. I hope everyone enjoyed the presentation as much as I did. Hope y'all enjoyed coming. We appreciate you, and hopefully we can have you back at some point.
Sounds great. Thanks so much for having us.
Thank you very much. Have a nice day.
Bye.
Thank you, everyone.
Bye-bye.